it doesn't seem very natural that the solution, the minimum rate of compression, is connected to communication over a noisy channel. But we'll see that these information quantities, these functions, are related to each other in some way, and we'll see various properties such as that some of these quantities are convex or concave, and what is the relationship between these, and so on. Okay, so let's start with the first problem that we're interested in, and that is the problem of data compression. So what is the data compression problem? We've already seen this in the previous class, but let me define this more formally. So the data compression problem is the following. We're given a file, which I'll call a source file. Let's assume that the source file has n symbols. Now these n symbols may be either bits, or you could treat them as a sequence of bytes, or a sequence of English characters or English words. So there are n symbols. Right, so n symbols, and each symbol xi comes from some alphabet, which I'll call script x, and depending on how you choose the alphabet, the solution to the problem can differ. So for example, let's suppose that we're interested in compressing English text. Okay, so we're given a text file, which we know it's going to contain English text. So there are different ways of treating this text file, of viewing this text file. Of course, this text file is stored on your computer, so you can treat this text file as a sequence of ASCII characters, right? So in this case, the alphabet would be the set of all ASCII characters. You could also treat this as a sequence of bytes, right? So it's a set of all so these are 8-bit strings, right? You could also treat them as a sequence of words, right? So sequence of words in the English dictionary. And so on. But what we will do is that we will treat this, so we won't really care whether we treat this as a sequence of ASCII characters, or a sequence of bytes, or a sequence of words in the English dictionary. So we'll take a very abstract representation of this source. We'll assume that it comes from some alphabet. For now, it doesn't matter what the alphabet is. Okay, but how you design your algorithms will of course depend on whether you treat this as a sequence of ASCII characters, or as a sequence of bytes, or a sequence of words, or a sequence of sentences. So our goal is to compress this text file. So originally this has n bytes or n symbols, and we want to somehow store this using less than n symbols, right? So our goal is to come up with an algorithm which we will call a compressor or an encoder. So this is a compressor or encoder. So this encoder is basically going to be a function which takes xn as input and outputs a sequence of k bits, right? So So Ck is a sequence of k bits. So the set of all sequences of k bits is going to be represented in this form. So it's 0, 1 to the k. And similarly, the input, the source file, is going to come from some finite alphabet. It's a set of n length strings. Right? So suppose that there was no compression at all, right? You didn't really care about compression. Then if you wanted to represent each symbol separately using k bits, or let's say that you wanted to represent uh, each sequence using k bits, then how small can you make k? So you have a sequence of n symbols, and your goal is to represent this in binary. Okay, so how many bits would you need without any compression?
Log n to the base 2.
Log n of what? Log n?
To the base 2.
Why?
Log base 2 of number of symbols we have.
Can you please repeat? Your volume is a little low.
Log base 2 of number of symbol we have.
Okay, and what is the number of symbols that we have?
That depends on the set, right? Like if you take ASCII character, then 26. If we take
So here I'm saying that my alphabet is script X, right? So tell me in terms of script X.
cardinality of X, like
Right, but I have n symbols, right? Each symbol is coming from script X. So how much would it be?
n log cardinality of X.
Yeah, so roughly n log cardinality of X, right? So it's cardinality of how many possible sequences are there? There are cardinality of X raised to the n possible sequences, right? And I represent each of these in binary. So I'll need roughly log cardinality of X raised to the n, or n log cardinality of X bits. Right? So without any compression, I would need k to be roughly n log cardinality of X. So more precisely, this would be the seal of n log cardinality of X, where this seal function denotes the smallest integer which is larger than n log cardinality of X. Right? So without any, so if there is no compression, then k would be n log cardinality of X. And of course, a good compressor is one for which k is something which is much smaller than n log cardinality of X. Okay, so now, so this is what the compressor or the encoder is supposed to do. Now it's not enough to just have a compressor. It's not enough to just store the file in some compressed form. We also want to be able to recover the original file, right? So what we want is another algorithm which is called the decompressor or the decoder. Right? So the decoder takes the compressed file as input and outputs xn or some estimate of xn. Right? So let's call it xn hat. Right? So we have, so the goal is therefore is to come up with a pair of functions f which takes xn as input and outputs a sequence of k bits. So f is called the compressor or the encoder, and we want another function which we call the decompressor or the decoder, which takes k bits as input and then outputs an estimate of the original file xn. And the hope is that xn hat is equal to xn all the time or roughly all the time. Okay. Any questions so far?
Sir, once
Yes.
explain n-log to cardinality of x. Once in basics.
Okay. So how many possible sequences are there? So each sequence comes from each sequence is of length n, and each symbol in the sequence comes from the alphabet script x. So how many possible sequences are there?
X.
So each symbol in the sequence, so let's treat each sequence as, so it's x1, x2, x3, so on up to xn, right? So this is my x superscript n, okay? And each, so x1 comes from this alphabet script x, x2 comes from the alphabet script x, and so on, right? So how many possible values can xn take?
X power n. Script x
So
power.
cardinality of x power n, right? Now you want to assign a binary sequence to each of these cardinality of x to the n possible sequences. So how many bits do you need?
Yes, sir, and I understood.
Right. So it's log of this, log to base 2, seal, because this may not be an integer.
Yes, sir.
So it's a seal of log cardinality of x to the n.
Thanks.
Okay. Okay. So any other questions?
Hello, sir.
Yes.
Sir, isn't the value can be less than that value log base to x raised to n?
So what value?
Because in previous lecture we saw that we took three number of 0, 1, 2 and we assigned 0, 0, 1 and 1, 1.
Correct.
So the average number of bits were 1.25 instead of 2 bits
Sure,
per.
sure. That is, of course, you're assuming a variable length scheme, right? So
Yes.
here, so right now we'll assume that k is fixed, okay? So I'm talking about no compression at all, okay?
Okay,
So we'll get to that in just a minute, okay? Okay.
Okay,
So right now we're assuming that k is fixed, okay? So k does not depend, does not vary with xn. Yeah. All right. Okay. So this is the problem, but I've not fully specified the problem yet. So if xn is arbitrarily chosen, then there's not too much that we can do at the moment. Okay. So what we'll do is we'll assume that xn is random. We'll assume that the sequence xn or the raw file xn is chosen from some probability distribution. So xn is going to be randomly chosen, and we'll assume, and at least for the purpose of this, for most of this course, we will assume that xn is in fact IID. It is IID with some known distribution px. Okay, so both the encoder and the decoder know that this is an IID distribution, and both of them know px. Okay, so f is in fact going to be a function of xn and px. G is going to be a function of ck and px, and this px is sort of site information that is provided and known a priori. Okay, so this is a simplifying assumption that we will make. So the two simplifying assumptions that we will make for now are that xn is IID and that px is known to both the compressor and the decompressor. Now in practice, this doesn't happen. Now, so for example, if you take English text, you can't really treat this as a sequence of IID symbols. And similarly, this distribution may or may not be known. Right? In general, it is not known, but it can be estimated from the input file. But nevertheless, for the sake of this course, just to simplify things, we will make these two assumptions. So it's IID and that Px is known. Okay, so that is given to us. Now the problem is sort of fully specified, and we want to ensure that k in some sense is as small as possible. Now there are two kinds of compressors, and we'll investigate each of these. So the first is what is called a fixed length compressor. So in fixed length compression, k is fixed. So what does this mean? So k depends on possibly on n and is allowed to depend on px, but not on the realization of xn. Okay, so once you specify what n and px is, xn is so k is fixed. Okay, and so for example, this simple scheme where you represent a sequence using log cardinality of x to the n number of bits, this is a fixed length scheme, right? It depends on n, it depends on, of course, the cardinality of x, but it doesn't depend on which file is actually being chosen. Okay. Now, on the other hand, we can have a variable length compression scheme as Sachin pointed out. Where k is allowed to depend on xn. So for some symbols, I could so maybe for one symbol I could assign the sequence 0. For another input it could be 0 0. The other input it could be 0 1, and so on. Right. So the length of the compressed file could really depend on xn. And in practice, this is what is generally done. So in practice, we have variable length compression schemes, as we also saw in the previous class when we tried to compress different binary sequences, all of length roughly 10 to the 6. We saw that for some files, the compressed length, the size of the compressed file was smaller, but for some sequences, the size of the compressed file was larger. Right. So in practice, we usually go for variable length compression, but fixed length compression is a very useful problem to look at, and it turns out that the optimal compressed lengths for both of these turn out to be roughly the same. So in the fixed length compression problem, so what is the goal? So k is fixed, and k is basically depends on n and px, but doesn't. But in terms of xn, the raw file, k is fixed. Right. So the rate of any compression scheme is defined to be k over n, So this is what we'll define as the rate of any compression scheme. And the goal is to keep the rate as small as possible. Right? So here's a question for you. Now suppose, let's look at a fixed length compression scheme and where I fix the rate. Okay, so K is fixed. And let's say that K is something which is strictly less than n log size of X. Okay, so K is strictly less than n log size of X. So do you think it is possible for any compression scheme to always ensure that Xn is equal to Xn hat?
There will be loss of information, sir.
Correct. And why will there be a loss of information?
Because we are going below the minimum bits we want to represent. So whenever we use decompressor, we will not get exact original value.
Correct. Correct. So let me elaborate on that a little more. So what is the compressor and the decompressor basically doing? So you have all possible sequences. Let me say x1 of 1, xn of 2, so on. So I'll just list out all possible sequences. Xn of size x to the n, right? So what is the compressor doing? For each xn, it's giving you a binary sequence, right? So this is my input space, right? And this is the space of all possible compressed files. So each compressed sequence is what I'll call a code word. So these are all possible CKs, right? So all possible K length binary sequences. So the all 0 sequence, 0, 0, 0, 0, 1, and so on. And what the compressor is doing, it's basically a function. So it's just assigning for each sequence on the left, it's assigning a sequence on the right. And clearly if K is less than n log the size of X, it's at least two sequences on the left are going to be mapped to the same sequence on the right. Right? And the decoder is basically never going to be able to distinguish between the two. It's not going to be able to say whether the true sequence was this one or it was this one. Right? And therefore, a fixed length compression algorithm with K less than log cardinality, n log cardinality of X is going to make an error. Yes, please.
The screen is stuck, sir.
Oh, okay. Is it? Can you see it now?
Yes, sir. It is lagging a little bit.
Okay, I see. Yeah, let me know if it gets too bad. Okay, so at what point did you lose this? So okay, so let me repeat. Now, what is the compressor doing? It's the compression algorithm or the encoder is basically a function which takes a sequence here and outputs a sequence from here, right? Set of all n length source sequences to k length code word sequences. And if k is less than n log cardinality of x, then at least two sequences on the left are going to be mapped to the same sequence on the right. And the decoder, when it observes this particular sequence, is not going to be able to distinguish between this sequence and this sequence. And therefore, it will always make an error whenever this code word is observed by the decoder. So whenever we're talking about fixed length compression, in addition to the rate, we also have to specify how much error we can tolerate. So the probability of error of a fixed length compression scheme is basically the probability that xn hat is not equal to xn, right? So here xn hat is the output of the decoder and xn is the actual file. So the goal of fixed length compression is to design this encoder and decoder pair such that the probability of error is below a certain threshold, some below less than some epsilon. At the same time, we want the rate r to be as small as possible, right? So typically what we demand is that as n tends to infinity, that the size of the input tends to infinity, we want the probability of error to go to 0. And as n tends to infinity, we want the rate of the compression scheme to be small. So we want the asymptotic rate to be small and the asymptotic probability of error to be equal to 0. It turns out that we can do both, and at the same time we can guarantee that that the rate is less than log cardinality of x. So this is the fixed length compression problem. In comparison, we can do better if we are allowed to do variable length compression. So note that k in this particular scenario, k is allowed to depend on xn, but now we want to ensure that xn hat is always equal to xn. So the decoder must always output the true file. It's not allowed to make any error. But since k depends on n, we can't really define the rate to be k over n because k is now a random variable which depends on xn. So k depends on xn. So what we will be interested in is in minimizing the expected compressed length. So the rate or the average rate will be defined as the expected compressed length divided by n. And we want to ensure that this is as small as possible. Okay, so any questions?
Sir,
Yes,
sir, in second case, k will be a random variable, right?
correct. So in the second case, k is going to be a random variable, and that is why I'm going to define the rate as the expected value of k divided by n. So the expectation is going to be a deterministic quantity. So of course, so as you mentioned, k is going to be a random variable for variable length compression, but for fixed length compression, it is going to be a deterministic quantity, and that is a distinguishing factor between these two types of compression algorithms. Any other questions?
Sir, then
Yes.
what about the distribution, sir?
So we don't know what the distribution is going to be, right? It depends on how you choose your compression and decompression algorithms. Depending on f and g, the distribution of k will vary. But our goal is to design f and g so that the expected value of k is as small as possible.
Okay, sir, thank you.
Okay, so maybe this is a good time to have a short quiz. So right now I'm going to post the link for the quiz both in the chat box as well as Piazza. You have it just has two very simple questions, and I'll give maybe 2 to 3 minutes to answer these questions. Okay,
Just before that, can we know the answers for yesterday's questions? We know it's so simple, but just to confirm.
Sure. So after this, let's go back. Let's discuss the last week's questions. Sorry, yeah.
Sir, do these have weightage?
Yes, these do. So I put up both in the chat box as well as on Piazza. So if you're not able to access one, you should be able to access the other. So I wait for just 1 more minute. Please fill in your answers by then. So for the previous quiz, I guess the first question was how many bits of information do you get if someone tells you the outcome of a fair coin? And the answer to that was 1 bit.
Sir, you're
Yes.
not sharing your screen.
I'm not writing anything down.
Okay, sorry.
I'm just mentioning just verbatim. So the first, if you remember the question for from the previous quiz, the first question was how many bits of information is contained in the toss of a fair coin, right? Or a Bernoulli half source, right? And that is exactly 1 bit because both 0 and 1 are equally likely, both head and tail are equally likely. So that's precisely 1 bit of information. And the second question was now instead of a fair coin, if it's a biased coin, with the probability of a head being equal to 0.3, then the answer is it's less than 1 bit, somewhere between 0 and 1 bit, but not exactly 1. And that is because you know that a tail is more likely, right? So you get slightly less information in this particular scenario.
Sir, can we be able to calculate the number of bits required because we already know the probability?
So you can. I haven't told you how exactly we are measuring the amount of information, and in fact that is what we will see in this lecture. Just give me a few minutes.
Yes, yeah. Thank
Okay.
So can we even discuss today's one?
Okay, just give me a minute. So I think you should have got. So please correct me if I'm wrong, but you should have got the solutions also, right? So once you answer, don't you get
Yes,
the correct answer?
Score as well.
Hello, sorry.
Yes, sir, and the score as well. Yes.
Yeah, the score and the correct solutions also, right?
Yes, sir.
Okay. So let me just check.
Sir, I'm not able to see quiz one question paper. Can you post it afterwards?
Sorry, what are you not able to see?
Quiz one paper, sir.
So which quiz?
The previous quiz, sir. Last week quiz.
Okay, it's there on Piazza, so you can take a look at it later.
Means it's showing already responded. Paper is not.
Oh,
You can't
okay, fine. So let me. Let me. Can you see this now?
Yes, sir.
Yeah. So if you tell the outcome of a fair coin, then you get exactly 1 bit of information, and if it's a biased coin, then you get less than 1 bit of information. But we'll now sort of quantify exactly how many bits.
Thank you, sir.
Okay. So let me share. Okay. So now that you've seen these two problems of compression, fixed length and variable length compression. For now, let's assume that. So now let's look at the case of variable length compression, right? So what do you think the optimal variable length compression scheme should be?
So can you please explain one of the questions in the quiz?
Sorry?
Can you please explain one of the question in the quiz?
Yes, please.
The answer which is 0, like.
Okay. Yeah. So one of the questions in the quiz was if okay. So suppose that the goal is say fixed length or variable length compression, right? And you can see my screen now, right?
Yes, sir.
Yeah. So let's suppose that px, so xn is deterministic. That is, px takes the value 1. Say for example, for a simple case, let's say that px takes the value 1 with probability 1 and any other value with probability 0. Okay. So no matter what, so no matter how many times you draw from px, you always get the same sequence, right? So if it's a deterministic sequence, then how many bits would you need? So what is the smallest k that you can achieve for this particular scheme, right? And the answer is 0, because now note that both f and g, both the compressor and the decompressor, know px, right? So irrespective of, so you
How will
know
it,
that,
uh,
yes, please.
how will the decompressor understand if there is file or not? Like 0 bit is nothing actually. So if you need to give a output or not give a output.
So when the decompressor is called, you assume that there is always going to be something that has been compressed, right?
Okay.
So here we're again we're abstracting the problem out. We're assuming that there is a file which has been compressed. So when the decompressor is called, you know that there is something that is going to be decompressed, right? So typically all of this extra information is usually stored. For example, what px is, what n is, maybe what k is. All of this will be stored as header information in the compressed file. And right now what we're interested in is in the remaining information, right? How much extra information do you have to store? That makes
Sir,
sense? Yes.
sir, can n be 0?
So if n is 0, then obviously k would be 0. Right? So if n is 0, then there's nothing to compress.
Okay.
So what we are really interested in is the case where n is greater than 1 and n is fixed. So n is known to the compressor and the decompressor. Right?
So
Yes.
in the variable and compression, we can even change the the characters itself.
What characters?
Suppose if you are using a symbol for specifying alphabet, say E, and we are sure that in every text, in the text we are given, after E there is an A.
Okay.
So we'll just denote EA as one character and use a symbol for it.
So once again, so the compressed sequence CK is always going to be a binary sequence, irrespective of what the source alphabet is, X. Okay, so that's number one. And if you know the statistics of the source, then indeed you could represent. So you could represent EA as using maybe 1 bit, and something else as a different sequence of bits.
Okay, sir.
Did I understand your question correctly?
Yes, sir. Like I mean to say, like, is the symbols always fixed? Like the characters which we are using should be always fixed. I
Yes.
understand.
So yes. So the alphabet is known, right? So that is how we are formalizing the problem. The alphabet is known and the distribution is known.
Okay, sir.
Okay. So basically, of course, here we're assuming that the sequence is IID, but in your case, when there is dependence, you know that, for example, Q is always followed by U, or E is always followed by A. And that is captured by the knowledge of PX.
Okay, sir. Got it.
Okay. Any other questions? Okay, so now let's talk about what an optimal variable length compression scheme should do. So any answers? So we're allowed to assign sequences of different lengths to different sequences, right? So what is the most natural thing we could do?
Depending upon the probability, we can assign the bits.
Correct. So what would you do?
The most uncertain, like least probability, we can allow more bits.
Okay.
If the probability is higher, which is certain, then we can allow less bits.
Okay. So what would be your algorithm to do this? So would you start with the sequence with the least probability or the sequence with the most probability?
Sir, with the most probability.
Right. So what would you do? You would sort the sequences in decreasing order of probability. So xn of 1 has the highest probability, let's say, and xn of 2 has probability slightly less than or equal to xn of 1. Xn of 3 has probability which is less than or equal to xn of 2, and so on. And what you could do is assign, say, bit 0 for xn of 1, bit 1 for xn of 2, 0 0 for xn of 3, 0 1 for xn of 4, 1 0, and so on, right? So again, so maybe just for convenience, I will number these as xn of 0, xn of 1, xn of 2, and so on. Okay. So this so what I claim is that this scheme is optimal, but maybe even before that, here I'm assuming that the length of the compressed sequence is somehow known to the decoder. So this is extra information, right? So I'm cheating in some sense. So for example, if the sequence, if the so the decompressor, what does the decompressor see? The decompressor will see maybe just 0 or 1 or 0 0 or 0 1 or something like that, right? And it has to output xn of 0 or xn of 1 or xn of 2. Now what I'm assuming here is that that the decoder has some way to know the length of the compressed sequence. And for now, we'll assume that let's say that this is stored as some extra information, maybe as the header of the compressed file. Okay. So given xn of I, what is the length of the compressed version of xn of I? How many bits does it take to compress xn of I? So note that for xn of 1, we use 1 bit. For xn of 2, we use 2 bits. Xn of 3, we use 2 bits, and so on.
Nearly log 2i, log I base 2.
So roughly log I to base 2, right? So I guess more precisely, so if let's take the original convention itself, 1,
Ceiling
2, 3,
of
and so on. Yeah. Yes.
ceiling of log 2i, log base 2i.
Are you sure?
Like, yeah, for 3 or log 2 of 3 will be like a 1 point something, 1 2 or.
Correct. But what about xn of 5?
Log it will be more than 2, right? So it will go to 3.
No. So xn of 5 is going to be, so it's 0 1 0 1 1, right? So xn of 4 is assigned 0, 1. Xn of 5 is assigned 1, 0. So it's 2 bits, right?
Okay.
Any other answers?
So round off to nearest integer.
Nearest integer. That may be right, but a little more precise. You can give it exactly in terms of I. I'm looking for a slightly different answer. You're close, but
So log I by 2 base 2.
not really. So okay, so the right answer is log I minus 1, floor of log I minus 1. Right, and this is for, of course, I greater than 2. So it's 1 bit for I equal to 1 or 2, and floor log I minus 1 for I greater than 2.
So that is when it starts from 0.
Which one?
Because when I equals 3, the value will be 1, but we have 2 bits, right?
Oh, right. You're right.
Even for 4 also.
Let me see. 3. Oh, sorry. I think this should be. Hang on. So xn of 1 gets 0, xn of 2 gets 1. Sorry. Does this?
So can we use 0 for 3?
Can we use
0 for 3?
Sure. Sorry, what is the problem with 0 for 3?
No, that's fine.
Right. So let's say, does log I plus 1 work?
Sir, it may be I plus 2.
Are you sure that log I plus, so floor log I plus 1 doesn't work for this case?
Yeah, I plus 1 seems to work.
Right. So in fact, I mean, I think this works.
Yes.
In general. Right, so the length of the compressed sequence is floor of log I plus 1. Okay, so I guess we're already over time, so we'll continue in the next class.
Sir, I
Yes,
just want
please.
to ask you something regarding yesterday's quiz. In the last class, we discussed about number of bits required. Information of x is number of bits required to represent x, right?
Correct. The minimum number of bits.
Yeah, expected number of minimum. Yeah.
Sure. Yeah.
So when we have a bias or a fair coin,
Mhm.
we would require one bit at least. Like, let's say probability of heads be A and probability of tails be 1 minus A.
Mhm.
But the number of bits required to represent both of them is, it will be A into something plus, like, let's say A is represented by 0, heads is represented by 0 and tails by 1.
Mhm.
We would still require one bit for both heads and tails, and by expectation is still 1, right?
Sure. Yeah. So that's a fair point. Right. So again, I guess I was a bit vague in what I mentioned in the previous lecture. But yeah, your point is well taken. So really, the information content for a random variable would to see this, you would need to take a sequence of maybe an IID sequence of random variables from that particular distribution, and see the minimum number of, and see the fraction of number of bits, or the minimum rate of compression for this particular source. Right? So that would give you the information content of that particular source.
Okay.
And if you view it that way, it is going to be less than 1 bit.
Yeah.
But as in question, you were asking about, for one trial, outcome for one trial. So
True.
one bit, the answer 1 bit seems kind of fair.
Sure. Okay. So anyway, the point doesn't matter. Okay, I'll give a grace mark for that. But
not regarding the score, but just to confirm, we take it that way and say that it has lesser information. We take a sequence and then say it has lesser information. But suppose one trial, will that also work then?
So again, it depends on how you define information more precisely, and I had not defined the information content very precisely. Right. So this was just a heuristic way of defining what information means, and really what we will define as information is going to be the information content in a random variable, as we will define, is going to be the minimum rate of compression for an IID sequence drawn from that particular distribution.
Okay, thank you. Yes.
So that is what we will say is going to be the information content of a source.
Thank you.
Yeah.
And sir, I have a doubt, not regarding what we have discussed.
Okay.
Yeah. In the first class, when we discussed about that there is a certain limit on how much data can be compressed, right?
Yes.
How much file can be compressed. So I was just wondering, suppose if we make a very complex hash map of, say, rather than taking each character, what if we take each word in a dictionary, every word in a dictionary, and create a very large hash map?
Okay.
And from that, let's say, then we would be able to decrease the size of compression to a very large extent, right? We would be increasing the size of the hash map that needs to be stored, but we would be decreasing the size of the compression, right?
Yes.
And suppose if we take, let's say, this is very far-fetched, but all the possible sentences of sorts,
correct.
Then we can even represent a very complex novel and just as the number of sentences it is, right?
Correct.
So will that also hold when we say there is a limitation, or yeah?
So the point is, now again, you have to be a little careful, right? So let's say that you use a hash map, okay? And that is precisely what a fixed length compressor is doing, right? You should exactly view a compressor as some sort of a hash map, although a hash has certain other properties of randomness and so on. But really, in some sense, that is the goal of a fixed length compression algorithm. But note that there is this dual problem, right? It's not that you just want to store something using fewer number of bits. You also want to be able to recover the original sequence from just the hash, right?
Yes.
So if you take too few bits, then you won't be able to reconstruct the original sequence, right? There is the probable so the fewer the smaller the size of your hash, the larger is going to be a probability of error. You agree?
Yes, sir. Yes.
Correct. So now, but still, your idea is good. So you can use a hash map, but let's say that we tolerate a very small probability of error, and the probability of error is allowed to vanish, but maybe vanishes slowly with n, right? Where n is the size of your text.
Yes.
So for example, if you do it for words, then maybe it's for sequences of length, maybe 10 or so, right? 10 characters, right? But for sentences, it's going to be much larger, maybe sequences of 100 characters. And similarly, you can try to create hash maps for essays, maybe a few thousands of characters, right? And as you pointed out, their compression, it turns out that the compression rate can be improved. So the minimum rate of compression that you could possibly achieve for sequences of length 10 is going to be larger than the minimum rate of compression that you can achieve for sequences of length 100 and so on. And even here there is going to be this fundamental limit. So since you want the probability of error to be small, you can't make the size of the hash to be too small. Once you fix the probability of error that you can tolerate, the minimum size of the hash that you can have automatically gets determined by that. That and the statistics of the source, of course.
Okay. Okay. Thank you. Yeah.
Right. Any other questions? Okay, so if you have any further questions, just put it up in Piazza and we can discuss it there. I will end the recording and the meeting here.